All right. So now it's showing recording, right?
Yes, sir.
Yes, sir.
Okay, so it's recording in the cloud, and I'll just have to Google and figure out how to retrieve it from there. But there has to be a way. So all right, so it's being recorded, right? Okay, thanks for pointing it out. I don't know if it was not why it wasn't recording before. Um,
Sir,
yes.
sir, is there any type of other function like we can consider in this model, or just we need to take this quasi-linear utility function, or why
We
have?
don't need to. We don't need to. As I said, right now we are being pretty relaxed about things. We are not trying to be very general, very rigorous. Uh, so I've taken a very special utility function at this point, right? We'll go much beyond this. We'll consider much more general utility functions later. Why have I taken the quasi-linear utility functions? Let me not answer that question right now. It will become clearer and I'll point it out. Why
Okay,
did I start with this special utility function? I'll try to give you a sense of that. Yeah,
okay, sir. Thank you.
Sir, can I ask a question?
absolutely.
Sir, what does the double derivative of UI imply?
I'll say that. I'll just hold your horses, right? You'll see soon the some of the implications of these assumptions that we are making.
Okay,
Right.
sir. Thank you.
Right now, I want to appeal to
So
their
last question.
realism. Yes.
So I had a question. Is QI a single good or a vector of goods?
Say that again.
Is QI a single good or a vector of goods?
Is UI
Is QI a vector of goods or a single good?
at this point? It's a single code. At this point, it's a single code. We'll come to all those generalities, right? Right now, things are very simple. QI is the quantity of wheat. Yes. Um, I've gone to the market. I want to buy some wheat, bring it home, make some chapatis, and eat it for dinner. Yes. So QI is the quantity of wheat, and MI. So both QI and MI are scalars, right? Once again, this is not the most general model that will be. This is a starting model to get
When
a
you say
case.
UI, QI is the utility out of QI good.
That's right. It's the utility just derived from the wheat consumption itself.
Okay, sir. Thank you, sir.
Mhm. Okay. Notice that P doesn't have a subscript I because everybody faces the same price. Um, okay, so now let's focus on the consumer's problem. And the consumer's problem can now be formulated if we want to postulate that this is a rational consumer, yes, then the consumer's problem can be postulated as a constraint optimization problem. The, the consumer has a well-defined utility function or well-defined motives or objectives, and she tries to make the most of it with her limited resources and means, right? Um, Now, let me just make a quick digression to say that this term rational consumers, rational agents, uh, is much abused, right, both by supporters and opponents of the standard economics paradigm, right? the when we say the consumer is rational, we mean it in a very specific narrow sense. We don't do, okay. So if a consumer says that I'm not going to save much for my post-retirement life, I want to live in the moment, um, uh, I want to take all the money that I'm earning now when I'm young and have as much fun as possible now. I don't care about my post-retirement years. Maybe I'll struggle then, but so be it, right? I can't think so far ahead. There's a sense in which many people might say that, oh, this consumer is being irrational. Okay, uh, that's not the sense in which we are using the term. So in our terminology, in this sort of economic analysis, We are not prepared to say that this person who's in the trade-off between current consumption and future consumption is making a choice tilted heavily towards current consumption. We are not prepared to say that this consumer is irrational, right? This consumer has a certain kind of preference and is making choices consistent with that preference, right? Uh, However, there's another consumer who, um, has enjoys pizza much better than pasta, but goes to the market and comes home with pasta, right? So that consumer has not made the best choice given her preference, relative to her preference, right? So in other words, in this sort of analysis, we are not going to question the preferences of the consumer. We'll respect that. We are not going to sit in judgment over that. The idea of a rational consumer is a consumer who can make the best choice given her preferences, right? Um, so, so keep that in mind. We are not saying that people are prudent, they're wise, they're always making healthy choices or always protecting their future. Those are matters of preference, right? So we are merely postulating here that whatever their preferences are, people can make the best choice relative to those preferences. Yeah. Questions?
Sir,
Yes.
does this mean that a rational person is someone who follows his preferences, so no matter if it is not conventional, but he is following his preference and making choice on the basis of that preference?
I'm really sorry. I'm not hearing you very well. But hang on just a second. Just a second. Let me try the earphones and see if it works better. Okay. Could you ask your question again?
Yes, sir. I was saying that we can conclude that if a person is following his preference and making choice under that preference, then he is rational, even if it is not conventional.
That's right. If he's making the best choice
Yeah, as
given
per
that
his
preference.
preference.
That's right. Right. So that's just terminology. That's the sense in which we are saying that our consumer, who we are studying, is assumed to be rational. Now, even that assumption can be contested, right? And has been contested. And there's a lot of debate about whether people can make the best choice, uh, even relative to their own preferences. And I'll have much more to talk about that. But at this point, we are assuming that. Yes.
Sir, exactly what is the meaning of best choice?
Best choice is that given your preference and given the set of things that you could buy or your budget set, you choose that, you make that choice which makes you happiest among the alternatives that you can afford, right? So you have a certain amount of money, let's say, and there's a certain basket of goods you could buy. uh, each basket gives you a certain utility. You you're a rational consumer if you always choose that basket which gives you the most utility, right? Most utility by your own
Got
utility.
it.
Okay. So here's the mathematical version of the consumer's problem, then, of a rational consumer's problem, if you will. Maximize overall utility subject to respecting the budget constraint, no theft, no stuff from outside. Now, it's very easy to see that this has to be binding, right? That you shouldn't be throwing away part of your income because you could have used it to buy either more wheat or more of other stuff. So, so this is equal. And then we can do a simple substitution, right? We can take this constraint optimization problem and convert it to an unconstrained problem. Now, that's very tempting to do, and we'll do it right now. But when we get to more complex versions of these consumers' problems, like many commodities, more constraints, at that point we have to use other mathematical techniques. This sort of simple substitution won't do. But for now, let's take the shortcut. Yeah. So what is the substitution? Mi can then be written as yi minus p of q, p times qi, right? So that's the substitution I've done. There's a small typo here, which I'll correct. This maximization with respect to the two variables, now we are maximizing only with respect to qi because we have substituted away mi. Mi has disappeared because of the substitution, right? Now, this is a very simple problem. If you're trying to maximize a function, right, a function attains a maximum where it gets to a peak. And what is, if you draw the tangent, if you draw the slope of the function at any peak, the slope is flat, right? So you all know that if you're finding the value at which a function attains a maximum, the answer is given by the point where the first derivative is equal to 0, right? That's the usual thing. So if we apply it here, we'll get this condition. The first derivative of the utility function or marginal utility equals price. Price comes from this component. When we differentiate it, we end up with P, right? So that's an important condition, that a rational consumer will keep buying that commodity until he hits the point where marginal utility equals price, right? And the intuitive understanding of that is very simple, very easy. Um, eh, Suppose, I'm going to the market and buying oranges. This is orange season, right? Winter, oranges coming from Nagpur and other places to our markets. So I'm looking to buy oranges. The oranges, let's say, the price is 10 rupees per orange. The first orange gives me 30 rupees worth of utility. The second is 25, and so on. Right? Let's say with every successive orange, my marginal utility falls by 5 rupees. So I'll keep buying, right? If I've bought only 3 oranges, that means my marginal utility is 20, right? So if I buy another orange, I'll get 20 rupees worth of value or satisfaction or utility, but I'll only have to pay 10 rupees. So that next orange is worth buying. So we keep buying till we hit this point, okay, where marginal utility is equal to price.
Sir,
Yes.
is this utility same as diminishing marginal utility or negative marginal utility?
This is
This this utility.
I'll tell you. Uh, there are two things. One is total utility, right? How much utility do I get if I, for example, consume 4 oranges, right? To get the answer to that question, you'll have to use the U function. You put Qi equal to 4 inside that function, and that tells you what's the total utility of 4 oranges. Now, I may want to also know that if I'm eating 4 oranges, what's the utility of the 4th orange, the last one which I bought and consumed, right? The answer to that is given by this ui prime, or the derivative of the utility function. That tells
No,
me,
no, sir. I'm asking this utility. DIS utility.
I haven't even used the term disutility, have I?
Oh, I was just asking very randomly.
No. So let's stick to the course, right? I mean,
Oh,
if it's a term which I haven't used,
all right, all right.
yeah.
Fair enough. Fair enough.
Okay. Right. So the intuitive idea is clear, right?
Sir, may I ask a question?
Absolutely, Lydia. Go ahead.
Yes, sir. So, in within the when we maximize the utility within the budget, subject to the constraint, we used an inequality rather than an equality. I get that, for generalization purposes, it might be better to use an
Right.
inequality, but in this particular case, would it be right if we used an equality for
Yes.
the
Okay.
constraint?
So let me explain that again, right? Now, this is the most general formulation, right? The consumer is free not to spend part of her money, part of her income, right? Or throw it away, or put it under the carpet. Um, Now, so that's why we wrote it like this, okay? But given our assumption that the marginal utility of both goods is strictly positive, right? In particular for wheat is also strictly positive. There's no point not using some of the income. Yes, that income will be used. So even if we start with this problem, the solution to this problem will be the same as a problem where in the constraint, we replace the inequality with equality. The two problems will yield identical solutions. Yes. So so
Thank you, sir.
so that's why we can, having written it in a slightly more general form, we can immediately switch to an equality constraint, and we are not going, making any mistake. Right?
Oh, all right. Oh,
Yeah. Now, you
thank you,
could
sir.
say that, thinking ahead a little bit, you could say, oh, people want to save for the future. So it's
Mm,
not like, so how come you're building a theory where you're assuming off the bat that a rational consumer will spend all the money? Well, if people want to save for the future, and if that becomes a central point of our analysis of the context, you could think of future spending as a good in itself, as a commodity, right?
oh,
Uh,
all right.
and
So,
and
so
so and so
that
then
is your
the
okay.
spending on the future, which is your savings, will become part of this constraint. And then once you
Mm,
define it that way, uh, after having bought goods for yourself today, after having saved for your needs in the future, after all of that, you shouldn't have any money left over. You shouldn't be
yes.
tossing out some of the currency in your wallet.
All right. Yes, sir. All right. Thank you so much, sir.
Yeah. Was there another question?
So basically, that is used for a general purpose. They're using that inequality sign, less than equal,
Yes.
just for a general purpose.
That's a more general formulation. But I'm saying that, again, right now we are being rather relaxed about our assumptions and this thing. So yeah, I started with the general one. But as I said, because given strictly positive marginal utility for both goods, this can be replaced by equality constraints without changing the nature of the solution. Okay. Um, right. Now, this is the optimizing condition, right? Now, you have to keep in mind, as you know, right, that a function attains a maximum at a point where its first derivative is zero, but a function also attains a minimum at points where its first derivative is zero. So first derivative is zero is a property both of maximum points of a function as well as minimum points of a function, right? If you draw a function, the peak has that flat slope, so does the trough. Yes, and so to check mathematically whether a function has achieved a maximum or a minimum at a certain point, we need a second criterion. And the second criterion, again, most of you will be familiar with this, is what is called the second order condition, right? If you think of a peak, that's where the slope is gradually decreasing, hits zero, and then if you go beyond the peak, the slope becomes negative, right? So peaks or maxima of functions, at least for simple single variable functions, have the property that the first derivative around that point is decreasing. That means the second derivative is negative, right? Whereas the troughs, the minimum points, have exactly the opposite property. That over there, the derivative, if you go from left to right, the derivative goes from negative to zero to positive, right? So the first derivative is increasing, which means the second derivative is positive. So if you try to identify a peak or a maximum of this consumer's objective function, then we need two conditions. One is that the marginal utility, the first derivative is zero, which gave us this, but also we need the second derivative to be negative, right? So if you take the second derivative of this function, this expression that we are maximizing, the second derivative is merely uh, ui double prime, isn't it? This part is linear. So if you differentiate twice, this becomes 0. This is a constant anyway. So we have ui double prime. Now, the we have a true optimum. To have a true optimum, we need ui double prime to be negative, right? Now, we have already assumed diminishing marginal utility. So if you're happy with that assumption, if we have all agreed to that assumption, then that assumption guarantees that the second order condition will be satisfied. Yes? So a consumer whose preferences uh, satisfy diminishing marginal utility, for such a consumer, we don't have to worry even about the second order condition. It is automatically taken care of by that assumption, right? If you don't make that assumption, then after applying this first order condition, we have to actually go and check whether at that point the utility function does have this uh, negative second derivative property, right? So uh, diminishing marginal utility seems appealing on empirical grounds that in most situations, maybe not in all situations, we might think that consumers satisfy it. But as I was hinting earlier, it has this additional benefit that if the utility function has that property, then the consumer's optimization problem is very well behaved. Wherever its first derivative is 0, that is a true point of maximum. Is that clear?
Yes, sir.
Yes,
Oh,
sir, it's clear.
okay. So now, you know, let's talk about demand functions. Well, consumers have demand functions. What are demand functions? Demand functions tell us that for a given income, a given price of the good, uh, I give maybe prices of other goods, uh, how much does the consumer want to buy? What is the consumer's demand? So the demand functions are basically obtained from the consumer's first order condition, right? So this equation implicitly contains the demand function. Ultimately, we want, if you want to write the demand function in explicit form, we have to invert this function, right? We have to express, we have to write it down in a form where qi is on the left hand side, and on the right hand side is all the other stuff, right? So qi is expressed as a function of price. Here it's not expressed in that way, but implicitly the demand function is already sitting here, right? Uh, if you take a particular utility function like log utility, for example, then you can see straightforwardly applying the marginal utility equal to price equation to this utility function, we can find the demand function, right? Uh, Now, um, one question which immediately arises is, can we say something about the shape of the demand functions, right? In particular, if you have a demand function and if you hold everything else constant, like the consumer's income, other prices, etc., and if you plot it only as a function of the good's own price, right? That is called the demand curve. If you draw a picture where everything else is held constant and you show the variation of demand with respect to the price of the good itself, um, that demand curve, can we say something about its slope? Is it downward sloping? Downward sloping demand curves would mean that if a good becomes cheaper, the consumer will buy more of it. If it becomes expensive, the consumer will buy more of it, right? Is there a good logical basis to make a claim like that? And that is often called the law of demand. This assertion that there's a negative relationship between the price of a good and the demand for that good coming from any consumer. Um, is there a good reason to make that claim, or uh, is the law of demand well founded? Now, for this particular model, which I emphasize is very special, right? this particular model, it turns out that immediately we can give a thumbs up to the law of demand. We can say, yes, if you buy these assumptions that we have made, quasi-linear utility, uh, the law of demand will be true. Okay, so let's do a quick proof of that. Um, so, and here I will use a technique, and that's why I'm starting simple, because I want to point out certain concepts, certain techniques, as I said, which we'll study later in much greater generality. But if you catch on here, it will be it will be easier for you to understand when we go to greater generality and abstraction, right? So pay close attention right now, what I'm going to say. Here's the thing. Uh, um, this is our consumer's first order condition for maximizing utility. Yes. Um, Given a market price, there's only a particular quantity which will satisfy this equation, right? If I carelessly throw in random values of Qi, this equation won't hold, right? That's why the equation is useful. It helps us identify the optimum Qi, right? The optimum purchase of a rational consumer. Now, uh, if I define Qi of P as the demand function, that is to say, the value of Qi which precisely solves this equation, the value of Qi which maximizes consumer utility, right? If I define Qi of P as the function which does that, and then I plug back that into this equation which I had, right? Then what I end up with is an identity. Now, this is a relationship which holds by definition, okay? So let me give you an example. What is the difference between an identity and an equation? So let's say, I write down uh, uh, x uh, minus 1 whole squared equal to 2, equal to 4. Okay. Um, Now, that is true only for a specific value of x, right? In particular, I'll have to use x equal to 5, for example. But if I write down the equation x minus 1 whole squared equal to x squared minus 2x plus 1, that's the formula for x minus 1 whole squared, isn't it? It'll be true for every value of x. So that's the difference between an equation and an identity. An equation is true for a particular value of x. An identity is true for every value of x. Yes? So if I have an equation, some expression of x on the left hand side, some expression of x on the right hand side, I cannot logically take the derivatives of the two sides and equate them to each other. That won't be true in general. But if I have an identity, then they're logically equivalent for every value of x. So for an identity, I can equate the derivatives of the two sides. That's the difference.
Sorry to interrupt you, sir. Sir, if can you use whiteboard for writing equations?
I
It
will.
would be clear.
I will. Today I haven't set it up. From tomorrow I will. Yes, I have a whiteboard which has arrived. So from tomorrow I'll use it. Right. Right now, just try to visualize it. If necessary, I'll use the whiteboard tomorrow to further clarify. But bottom line at this point, that once we have an identity, we can take the derivative of the left hand side and the derivative of the right hand side. Those two derivatives will also be equal. So will the second derivative, so will the third derivative, because they're logically identical objects on the two sides. Yes. So coming back to this context, once I use the demand function, I use Qi as a function of P, that value of Q which solves the first order condition, then this becomes an identity, and I'm allowed to equate the derivatives of the two sides. Derivatives with respect to P, right? The only variable which is remaining. So if I take the derivative of the left-hand side, I have to use the chain rule, right? First, the derivative of the function with respect to its argument, that gives me Ey double prime. And then further the derivative of what's inside, which is Qi prime of P, right? That's the slope of the demand function. So all of that stuff equals derivative of the right-hand side, which is 1. And now, just by switching terms, I can express Qi prime as 1 over Ui double prime, right? The second derivative of the utility function. Now, remember that we assumed diminishing marginal utility, yes, which means second derivative is negative. So again, if we are prepared and happy to make that assumption, it implies logically, in a watertight deductive way, the law of demand, right? So again, remember at the beginning we were discussing that other than realism, what does this assumption give us? Well, this assumption gives us two more things. One is that it guarantees our second order condition is going to be satisfied, as we discussed a moment earlier. And it also guarantees, it helps us make sharp statements about the nature of the demand function, in particular that it's downward sloping, that the law of demand holds, right? Of course, we can't get something out of nothing, right? In any economic model or analysis, if we want to reach sharp conclusions, we have to make certain assumptions, right? What the theoretical analysis shows us is that what kind of assumptions leads to what kind of conclusions. And if we examine the assumptions and find them to be plausible, to be, maybe we can believe it holds for most people in most situations in markets, then we can have a lot of faith in the conclusions, right? So what we have seen here is that there's an intimate connection between diminishing marginal utility, that assumption, and the law of demand, right? That assumption implies the law of demand. Okay, so now everything rests on that assumption, that if you like that assumption, then we'll have a strong faith in the law of demand.
So, would you mind repeating the second point? The identity thing.
Okay, so the general point there is, first of all, there's a difference between equations and identities. Yes. Let me state the sort of bottom line clearly, and then tomorrow when I use the whiteboard, I can further elaborate with examples. The bottom line is this: in an equation, you have some function of x on the left-hand side and another function of x on the right-hand side. It will be wrong. So let's say fx equal to gx. F is a function of x, g is a function of x. And it's an equation, right? Meaning that it's true only for certain values of x, not for other values. Then I cannot write down that f prime x equal to g prime x. That will be wrong. I cannot take the derivatives of the two sides of an equation and set them equal to each other. But if fx equal to gx was an identity, if it was true for every value of x, then it will always be true that f prime x equals g prime x. Okay, so if you want me to satisfy that claim to you with examples, I will do that tomorrow. Right? But that's the bottom line. That once we can arrive at an identity, we can equate the derivatives of the two sides, and not just the first derivative, the second derivative, the third derivative, and so on. Right?
I get it now.
Yeah. So that's why so once you appreciate that, and then if you look at this identity, right? This is an identity because it is true by the definition of the demand function. The demand function is such that the quantity derived from the demand functions satisfies marginal utility equal to price, right? And that's how we got to that point.
Yes, sir. Thank you so much.
Yeah. Okay, any questions at this point? So what we are using here in a very simple form is what is called the implicit function theorem, right?
Sir, can I ask a question?
Absolutely.
Sir, while we were maximizing utility, we still equated the derivatives of our like marginal benefit equals to or marginal utility is equals to price. However, it was not an identity.
Right.
So, sir, you just said now we cannot equate derivatives of an normal equation or
Yes.
but we can only equate derivatives of identity. But we did the same in maximizing utility. So why is it so?
So there's a subtle difference. So when I've gone back to this previous slide, right? So when I wrote this, this was an equation. Why was this an equation? Because not every value of Qi will satisfy this equation. Only a specific value of Qi will, right? So that's why this was an equation. Now, uh, now we are defining the function Qi of P as precisely that value of Qi which satisfies this equation. It is the solution to this equation, right? Now,
Yes, sir.
once I insert that solution into my marginal utility expression, then this equation, then this relationship has to hold by definition,
Okay, sir.
right? An identity is an equation which holds by definition, which is true for every value of the variable or variables. X plus y whole squared is x squared plus y squared plus 2xy. No matter what value, what any real value of xy you plug in there, that equation will always hold. That's what makes it an identity. And once we insert the solution to the equation, that's why it gets transformed into an identity.
Okay, sir. Got it.
Okay.
Thank you, sir.
Yeah. All right. So now let's talk about this. It came up earlier, but eventually we are, as I said, if you take a couple of steps back, and as I was discussing with that example yesterday, all of this analysis, it starts with, okay, what are people's motives? What are agents' motives? What are they trying to achieve? That leads to, what can we say about their behavior, their choices, how they will respond to various things like price changes, income changes, and so on. And that leads to market outcomes, aggregate, what will be the prices, quantities in the market. But the further step along that way is to ask, if you leave things to markets, is the outcome good? Should there be some sort of government intervention? So to evaluate, whether something is good, we have to again go back to the individual and say, what does the individual gain from participating in this market transaction? We need a well-defined measure. We need a concrete notion of what the welfare gain is from any transaction in the market. So that's where the notion of consumer surplus comes in, right? So even in this very simple framework, we can define it the following way. See, if compare two situations, one in which this market for wheat doesn't exist, right? In that case, the consumer will have to spend all the income on other goods, right? So that MI, money spent on everything else, will be equal to YI, income. And that'll be the utility, given our quasi-linear utility form. Now the market opens up and the consumer can opt, and the price is P, and the consumer can optimally choose her purchase, her demand. Then the consumer's utility is this, right? This is the utility from wheat, and the money spent on everything else is income minus whatever has been spent on wheat. Okay. So what is the gain? What is the addition to utility when this market opens up? Well, the post-market, the post-transaction utility, which is this expression, minus the utility that would have happened if the market remained shut, right? Which is YI. So subtract yi from here, it cancels out. And so essentially, this is our measure of uh, how much the consumer is gaining from participating in this market, right? Now, this can be written in a form which might look weird at first glance, but it kind of makes sense and easily lends itself to drawing pictures, right? Now, remember, for any function, if I differentiate the function and then integrate it, I get back the original function. Isn't that true? Right. Um, so therefore, instead of writing in this form, I can write it in a more convoluted and apparently strange fashion, which is this. I differentiate it first. Okay. Um, and then I'll integrate it from 0 to the point of purchase, right? The relevant quantity which the guy buys. Now, if you look at the second line, the last line, right? This is the difference between marginal utility and price. So in some sense, the gain to the consumer is the difference between marginal utility and price up to the quantity that the guy actually buys, right? So um, what does this mean in diagrammatic terms? First of all, um, first of all, um,
Sir,
yes.
can you explain the last equation again? The integration one.
Okay, you are happy up to this point, right? That
Yes.
this is a good measure of consumer surplus, the gain to the consumer from participating in the market.
Yes, sir.
Okay. Now, purely mathematically, right? If I have a function f of x, if I differentiate it, right, f prime of x, uh, and then I integrate it from 0 to x, right? So I'll say, okay, f prime of, change the name of the variable, f prime of y, and I am integrating it from 0 to x. Right? Integration and differentiation are reverse operations, right? Uh, so if I differentiate a function and then integrate the function, I get back the original function. Yes?
Yes, sir, but why did we do it?
You have to hold your horses a little bit. I'll show you why we do it, right? As I said, that we are doing it so that we can transfer this measure, which we assume is a good measure, uh, into a diagram. Okay. Let me let me say one thing at this point. When you're trying to understand economics, um, there are sort of multiple ways in which we try to understand a concept, right? Uh, Sometimes we draw pictures, sometimes we do some mathematics, and sometimes we talk intuitively in terms of the people and going to the market, buying stuff in plain English. What I want you to sort of really internalize is the ability to understand the same concept, the same issue, using all of these three different techniques, right? You should be able to say, okay, this concept in terms of pictures means this, in terms of maths means this, and in plain and simple English language, it means this, right? And that is what I'm trying to develop here. I'm trying to show you the connection instead of just sort of blurting out, okay, consumer surplus means area under the demand curve. I'm trying to show you the logical connection between the maths, the pictures, and the words, right?
Okay.
And I'll keep trying to do that repeatedly. And this is something that you need to internalize. As I said yesterday, take a very different approach. Don't memorize formula, rules, laws, etc. Try to understand. And if you really take that approach, you'll find the course much, much easier. Yes. And that's what I'm trying to build. So you'll see in a moment why I did this. Okay.
Okay. Thank
The
you.
over the larger answer is to draw the connection between the maths and the picture. Okay. So now, having written it this way, look closely at what is what is it that is being integrated, right? What is being integrated is the difference between marginal utility and price. Okay. So if I draw a marginal utility curve and if I draw a price line, the area in between that two, that is precisely what this integration is. Okay. Now, one last thing to complete the translation or the transition to the picture is, how am I doing on time? Okay, I have just 2 minutes, so I'll do this, say this, and I'll wrap it up. Uh, Remember, if I draw a marginal utility curve, right, first derivative of the utility function, that essentially serves as the demand curve. Does everybody see that? Because the consumer's optimizing principle is price equals marginal utility. So on the horizontal axis, take any price. How much will the consumer buy? Well, you have to go to the marginal utility curve and read off the value on the quantity axis. Right? So essentially the demand curve and the marginal utility curve are identical. Right? And now, as we saw, the consumer surplus is given by this expression, the gap between the marginal utility curve and the price line. So take any price, forget this, whatever this is. Take any price, say at this level, okay? The demand curve is our marginal utility curve. This is the price line. So that formula we derived, that integration, essentially is capturing the area in between the two. Yes? And so diagrammatically speaking, this is our consumer surplus. Mathematically speaking, it's these expressions. In terms of pictures, this is our consumer surplus, right? In terms of intuition, how do we map it to intuition? Well, what is the demand curve really capturing? There's two ways to read the demand curve, right? One is that at a given price, how much will consumers buy? So you start from a point on the vertical axis and arrive at a point on the horizontal axis. Another way to read the demand curve is to go the following way. For any quantity, what is the value of the marginal unit to the consumer? And therefore, what is the price the consumer is willing to pay to buy that amount? Right? So that interpretation takes you from the quantity axis to the price axis. So think of the second interpretation, right? That if I think of quantity in small amounts, quantity of 1, 2, 3, 4, 5, 6, so on, the height of the demand curve really captures the value of these successive units to the consumer, right? The height at 1 is really the monetary equivalent value of the first unit of the good. The height at q equal to 2 is for the second unit, and so on, right? So think of the first unit. The value of the first unit is captured by the height of the demand curve, but what the consumer actually has to pay is given by the price line. So that difference is, if you will, the consumer's profit or surplus from buying the first unit. So total consumer surplus is obtained by adding up all these vertical differences between the demand curve and the price line. And that's how we arrive at this area.
Sir, can you please explain the second interpretation again?
The last interpretation is trying to give you an intuitive sense of, why this area is consumer surplus and a good measure of the gain of the consumer from the transaction. Well, here's how it goes. Think of the demand curve as, first of all, instead of a continuous variable, let's think of it as, small little units, 1, 2, 3, 4. Okay. The height of the demand curve at q equal to 1, what does that capture? It captures the value of the first unit to the consumer measured in money, right? So at q equal to 1, if the height is 20 and the price here is 8, right, then that gap of 12 is how much the consumer gains when she buys the first unit. right? See, she's getting something worth 20 rupees, which she would have been happy to pay 20 rupees for, but she's actually paying 8. So the first unit she buys fetches her a gain or a surplus of 12. And that's the height between the demand curve and the price line. But she doesn't stop at buying the first unit, right? So now she buys the second unit. And suppose the height at Q equal to 2, the height of the demand curve is 15, let's say. The price is still 8. So the second unit she purchases gives her another sort of gain or profit or surplus of 15 minus 8, 7. Okay. So she made a profit of 12 on the first unit she purchased, and another profit of or a surplus of 7 on the second unit she purchased, right? So already she has gained 12 plus 7, 19. And she keeps going on like this, buying successive units until she arrives at this point, right? So if we now try to measure the total surplus, total gain of the consumer from participating in this market, it's the sum of the gain from the first unit, the second unit, the third unit, etc., 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 up to this point. And if I'm adding up all these vertical distances, right, and then basically what I'm getting is this area, this triangle, which we labeled in a picture as consumer surplus, right?
So the measure of gain, purely mathematically speaking, could be negative as well. I mean, the second last equation that we had.
Absolutely, it could be negative, except that it will never be, because the consumer is rational and is choosing rationally, right? One option that the consumer always has is not to buy anything at all.
Exactly. So if it's negative, it's zero. I mean, intuitively speaking.
Yes. So take a situation where the price, right? So this is the marginal utility curve. So it starts at this height, let's say 20. And suppose the price is 25. The price line is entirely above the demand curve or the marginal utility curve. Then the consumer will choose a corner solution, will choose the amount 0, right?
Okay.
So the consumer surplus can never be negative. I mean, in principle, it can be negative, but that requires the consumer to make a mistake.
And to be like exact, I mean, not the assumption, I mean, not taking the assumption of rational consumer, that is pretty much possible, right, in the real world?
That becomes an empirical question. I mean, yes, there's questions about, how there's a book by Naomi Klein called No Logo, if some of you have seen it. And the basic point is that, advertisers brainwash consumers.
Okay.
So let me not answer the question definitively, right? You can make your own guess. Yeah, we can talk about more. We'll have as we develop the theory, we can have breakout sort of discussion times, and those will be times when we can discuss this question. The answer to the question is very open ended, right? Yeah, sometimes yes, sometimes no. I don't know. I mean, we can have different viewpoints on that.
We've never had economic theory beyond rational consumers, so probably it's something to think about.
No, that's not true. I'll show you in this. Although my mandate is fairly limited, I'm doing very traditional classical stuff. I'm not getting into the more fancy modern theory, game theory, information economics. Even then, I will show you when I discuss a model of hyperbolic discounting. There again, the term rational is very tricky, but in a certain sense, I will show you where modeling approaches, theories, where we deal with people who have internal conflicts, who regret their own choices, who have self-discipline problems, and so on.
Thank you, sir.
All right. So I think I should let you go because I've run overtime, and so we can have more Q&A tomorrow. You probably have. Do you have another lecture now?
Yes, sir.
Yes. So let me stop here and not hold you up any further. So see you tomorrow.
Okay, sir.
Okay.